Okay, this lesson is on the mean value theorem, and actually the mean value theorem is one of the most interesting theorems that you see in calculus. And when I say interesting, I know that can sound scary, like as if something's going to be difficult here, but actually I find the mean value theorem to be a little bit difficult to access initially, but then it's almost like it's too easy. Some of the results today will be like, isn't that just really simple? And so if you get that feeling as you go along, is that for a while you're like intimidated and then all of a sudden it gets real easy. That's about what the mean value theorem is supposed to be like. So that's about the right place to be with the mean value theorem. Anyways, let's not get too carried away with the introduction. We'll get right into the mean value theorem. But to really get it, I want to start with a sort of basic example that I hope will seem really obvious as I develop it, and that will be a great jumping off point. I just want you to imagine I decide to get in my van and take a long drive. So very simple situation, just getting in my van, driving down the road, and here comes my van picture again. Some other videos you might have seen this. It's the only real picture I can draw there. So there I am driving in my van along the way. And let's just imagine that I go on a journey, and I don't really say much about it, except that I end up driving 180 kilometers. And this journey takes me 3 hours. Okay? And I've made the numbers work out very nicely here. So that means the average velocity for my trip, I went 180 kilometers. It took me 3 hours to do it. And so I get an average velocity of 60 kilometers per hour. And now I get to the main part of my argument, is that if my average velocity along this trip was 60 kilometers an hour, I argue that I must have been going 60 kilometers an hour somewhere along the trip. That may seem perfectly obvious. When I say that, you might, well, of course you were. But let me just really argue it so that it's very, very clear that that is true. If my average velocity for the trip was 60 kilometers an hour, there are, I think, only three possibilities. That is, I started my journey at 60 kilometers per hour. That is, right there at the start, I start at 60 kilometers an hour, and my average velocity ends up being 60 kilometers an hour. Well, then it's trivial, yes? If my average velocity was 60 kilometers an hour, and I was driving 60 kilometers an hour at the start, then at some point I was driving 60 kilometers an hour right at the start. Okay, so that's not interesting. Maybe I started faster than 60 kilometers an hour. That's the other possibility. So these are the starting possibilities. Maybe I started faster than 60 kilometers an hour. Well, I argue if I started at 60 kilometers an hour, at some point I'm going to end up with an average velocity of 60 kilometers an hour. I'm going to have to go slower than 60 kilometers an hour, which means at some point in between, I'll have to have gone through 60 kilometers an hour. There's the mean value theorem. I got to tell you, that's the mean value theorem in a nutshell. If I end up with an average of 60, and I start with more than 60, at some point I'm going to have to go less than 60, which means I'm going to have to go through 60 at some point. See, in between there, the mean value, to get that average somewhere in between, I'm going to have to go that 60 kilometers an hour. Well, the last one, if you get that, the last one's not exciting at all. Let's say I start slower than 60. And if I start slower than 60, at some point I'm going to have to go faster than 60 to get my average back to 60, which means at some point I'm going to have to go through 60. Let's use some specific numbers. Let's say I start off at 80 kilometers an hour. But my average velocity is only 60, which means somewhere along the way I'm going to have to go slower than 60 for a while, which means at some point in the middle there, I'm going to have to hit 60 as I slow down to that slower speed. Again, if you're like, well, isn't that pretty obvious? Well, mean value theorem can be like that. There's moments in the mean value theorem where it's all of a sudden, isn't that an obvious thing? Well, let's jump into the technical version of the mean value theorem. And the technical version says if y equals f at x is continuous at every point. That becomes important later. Let's talk about that later, why it has to be continuous. And differentiable on every point on the interior of AB. So we've got some interval a to b where it's both continuous and differentiable. Those are important qualifications. The mean value theorem can fail, and I'll talk about that in a later slide, how it can fail. But it can fail. But if it's continuous and differentiable, then there's at least one point in there where the derivative is equal to the average. That's what this is. This part here is the average rate of change. That is, it's the slope of the secant. They've gone f at b minus f at a over b minus a. They said, okay, the average rate of change is what's calculated on the right-hand side. And what the left-hand side is saying is at some point you have to have that slope. Okay, if that's confusing, let me really break it down. There's at least one point in the interval where the tangent slope is equal to the secant slope from a to b. There's at least one point where the instantaneous rate of change is equal to the average rate of change. That's what I was saying in the opening slide there. Well, let's get a picture of what's going on here. Let's say you got some function y equals f at x, and I've drawn a function here, but you don't really need a specific function, but that's a good to look at here. And you got some initial point, a comma f at a, and some final point, b comma f at b. If I draw a secant through those 2 points, and find the average rate of change from a to b, then there must be some point. Okay, that slope there is missing some minus signs there. That slope between those 2 points on the secant slope is f at b minus f at a over b minus a. Nothing weird going on there. There's just y2 minus y1 over x2 minus x1. If that's the average rate of change, somewhere in that interval, it must actually have that slope. That is, it must have that tangent slope. And I make the argument the same way I did in the previous one, is that if the slope starts out, like this one does, the slope starts off lower than the actual slope. If you look right here at A, the slope here is a lower slope than what the actual secant slope is. If you start off lower, at some point you're going to have a higher slope, which means you're going to, at some point, somewhere in the middle there, you're going to have a mean value in between there. Well, you're going to match up with the mean value, and you're going to get that tangent slope to be equal to the average rate of change over there. So this slope is f at c. Let me just go over that one more time. If you've got an interval and you find the average rate of change over that interval, somewhere in between, you're going to have the tangent slope equal to that slope. And there's only 3 possibilities. You either start off with that slope, or at some point, at the start, you start off with a lower slope, in which case you're going to have to get up to a higher slope. So if you're going to go to a higher slope, so there's the lower slope there. If you start off with lower, you're going to have to end up with a higher slope, and which means somewhere in between, you're going to have to hit the same slope in between. So here's the mean value theorem for derivatives, and this is just using the derivative in there. In that same picture, we're going to actually have the derivative in there. Oh, that's f prime. That little prime was missing there. So, if y, this is the same statement as before. So how do we use the mean value theorem? Here's an example of how we use it. So if it's not perfectly clear, check out this example, and I would do it on a separate page here so you can see it. Show that the function f at x equals x cubed minus 3x squared plus 5x minus 7 satisfies the mean value theorem. So what I'm going to do is I'm going to find the slope of the secant. That is the average rate of change on this interval 0, 2. So on 0, 2, slope of the secant will be f at 2 minus f at 0 over 2 minus 0. I'm just going to find that slope between 0 and 2. Like really just the grade 9 version of this question, where I'm going to find the slope between y2 minus y1 and x2 minus x1. So if I plug in 2 to that, let's see, I get 8 minus 12 plus 10 minus 7. I've just subbed 2 into that function there. And then I sub 0 into that, and I get negative 7. And then the bottom is 2 minus 0. And when I plug all this in, I get 6 over 2, which is 3. And what I mean by that, I'm going to draw a little tiny picture of that, is that if you go from x equals 0 to x equals 2 on this curve, I get slope 3. Now, I don't know exactly what this function does. Maybe it goes up and then goes through there and then goes through there, something like that. I don't really know exactly what it does, but I do know the slope of the secant between these 2 points is 3. So let me just write that down. Slope of the secant equals 3. So, to satisfy the mean value theorem, then what I need to say then is, therefore, f prime at x equals 3 between 0 and 2, somewhere in there, it must match up and actually have slope 3. And in my diagram, now I don't know if I've done the right graph here or not. In my diagram, you can see somewhere there it's going to have that slope. So what is that point? Okay, so f prime at x will be simply 3x squared minus 6x plus 5. So when does f prime at x equal that 3 that I'm looking for? So I get 3 equals 3x squared minus 6x plus 5. And I'll bring that over. I get 0 equals 3x squared minus 6x plus 2. And this doesn't factor, so I'll need the quadratic formula. So I go x equals negative b plus or minus square root b squared minus 4ac all over 2a. And when I do this, I get x equals, let's see, 6 plus or minus square root 6 squared minus, let's see, 4 times 3 times 2, minus 24 over 2 times 3. And I think I get these two values, 6 plus or minus square root 12 over 6. When I get those as a decimal, you can punch them in your calculator and check. I think I get 1.58, or x equals, punching that into my calculator here, 0.42. That's what I get. So actually it happens twice. You actually get that sloped twice in between there. Now, the mean value theorem doesn't say it has to happen twice. It says it has to happen at least once. But in this particular example, I got that it happened twice. Therefore, yes, it does work. F prime at x equals 3 twice in 0, 2. And again, it didn't have to be twice. It only had to be once to satisfy the mean value theorem. So something about this graph means this graph must have gone above that slope for a while, then below that slope for a while, and then came back again, sort of gone back and forth in there. Okay, so let's just review what we've discovered. If the average rate of change over some interval is 3, it means somewhere in there the tangent slope must have been 3, and we found out what that specific x value was. Back to the mean value theorem. I just want to talk a little bit more about when this can fail, because it said it had some rules in here. It has to be continuous and it has to be differentiable in that interval for this to work. And how can it fail? Let's look at a couple cases where it could fail. The first one is, take a look at that absolute value function that you see here, and that is not differentiable. At x equals 0. So there is a point between -1 and 1 where this function is not differentiable. And then we have on the right-hand side, we have the function int, and so it's not continuous. at x equals 2. Well, a lot of other places too, but it's not differentiable at x equals 2. And so what we say there is these two functions might break the mean value theorem. The mean value theorem might not work because the slope jumps here. For instance, on the left-hand side, the slope goes for -1 and it jumps all the way to +1. So it doesn't get all the slopes in between. So we sort of implied at the start of this that you would get all of the velocities. When I was talking about my van, we sort of said, well, if you start with a velocity lower than 60 kilometers an hour, at some point, if you want to get a velocity above 60, you're going to have velocity 60 at some point. That's the whole thing about differentiable, is that you need to smoothly go from one slope to the next. And so when things aren't differentiable, then we don't get those seemingly obvious results. You don't get these situations where it's like, oh, well, if you're going to go from below 60 to above 60, you got to go through 60. That is absolutely true if things are differentiable. But if they're not differentiable or they're not continuous, then you can jump past them. So there's an example that I want to show here. Show two functions that fail to satisfy the mean value theorem on the interval -1 to 2 for some reason. Well, I did it on a separate page here, but let's just talk about that absolute value function again. And see, I've got this function here. And I look at, say, the value at -1 and the value at 2. And you see there'd be some slope there between -1 and 2. Over to 2, 2. So the slope here would be 1/3. I'm just looking at that and going, okay, rise 1, run 1/3. But there's no way, slope with a secant would be 1/3. But there's no point in between where that slope is 1/3, because the slope on the left is always -1 and the slopes on the right is +1. And for a second you're like, oh no, the mean value theorem didn't work. Well, the reason it didn't work is because it was not differentiable somewhere in between there. So the mean value theorem can't fail if it's not differentiable. And the int function does this too. The int function would look like this on that interval. See, it's there, and then it's there, and then it's there. And so the int function would have these values, -1, -1, and 2, 2. So it would have slope of the secant equal to 3/3. It would have slope of the secant equal to 1. But as you can see, the slope on every point here, every slope of the tangent would be 0. So then you don't get that just because the slope of the secant was 1, that you don't get that the function actually has slope 1 anywhere. And why does that happen? It's because this function is not continuous all the way through. So that's why those rules were there. Back to the rules. The mean value theorem works as long as this function is continuous and differentiable going through there. Okay. If it is not continuous or differentiable, then the mean value theorem can fail. So some quick results from the mean value theorem. It can be used to do some proofs that are fairly easy proofs to think about, but maybe are technically a little bit difficult. One is this corollary, and a corollary is a result that follows from another theorem with very little proof. There's not much we have to talk about here to prove this. Let f be continuous and differentiable. Okay, so those are those qualifications that have to be in there for the mean value theorem to work, is that things have to be continuous and differentiable. And the result is, if f prime at 0 at each point, then f always increases. That may seem obvious. In my brain, that's obvious. If f prime is greater than 0 at each point on AB, then f must increase. And vice versa. If f prime is less than 0, then it decreases. But to actually prove it can be a little bit difficult, even though it seems obvious, without the mean value theorem. But with the mean value theorem, it's pretty straightforward. Let x1 and x2 be any 2 points with x1 less than x2. So I'm just going to draw a little picture of what's happening here. There's some x1, and then later on some x2 like that. The mean value theorem applied on here says that, well, it's been rearranged here. Here's the mean value theorem. Back to here, mean value theorem. right there. And in this case, what they've done is move that, I've sort of cross-multiplied here and said there's another way to state this, is f at b minus f at a would be equal to f prime at c times b minus a. They've just moved that b minus a over to the other side and restated this by moving that b minus a over. So that's why that looks different. It's really the same thing, but they've just moved it around there. And what they've said here is the mean value theorem applied on x1, x2 says this, just moved around. For some c between x1 and x2, the sign on the right-hand side of this equation is the same as the sign of f prime at c. Well, what they're saying there is x2 minus x1 is always going to be positive, because if you look in the diagram, x2 is bigger than x1, and f prime at c, then we'll decide. If in the first case, if f prime is greater than 0, this will be positive, which means this has to be the bigger one. If that side is positive, that means f at x2 would have to be bigger than x1. So that proves that it would be increasing. However, if f prime at c happened to be negative, then that side would be negative, and then this one would have to be the smaller one. And so then f is decreasing. So fairly simple here, hard to get by the symbology here, but fairly simple, is that if f prime of c is positive, that is, if we're always positive in that section, that's what the A part says, is f prime at c is positive. If that's true, then we will see that every f at x2, every y value will be bigger later on. And now if the opposite is true, if f prime at c is less than 0, that's what the second case says, and then we're talking about a negative derivative there. If you have a negative derivative every time there, then the right-hand side will be negative. And that means that if you look on the left-hand side, that function value at the second x value will have to be less. And so then you will get a decreasing function. Another corollary, if f prime at x equals 0, so if you get a derivative of 0, then there's a constant c where the function is equal to that constant. Again, this is such an obvious result to me, is that if the derivative is 0, the function must be a constant. But difficult to prove. Actually, sort of difficult to prove, but the mean value theorem does it in just a couple of steps. Our plan is to show that for any 2 points, x1 and x2, that f at x1 will be equal to f at x2, that the y values will be the same. And again, we're going to assume that they're numbered x1 and x2, and that x1 is smaller than x2, like that. Now, since it's differentiable and continuous, since it's differentiable, see, f prime at x equals 0 implies that it must be differentiable. It's saying that we can find the derivative, and that derivative is 0 all the way through here. So this thing is differentiable. Then it also must be continuous. If you're going to be differentiable, you have to be continuous. So then f satisfies the mean value theorem, that is, there is a point somewhere where f prime at c equals f at x2 minus f at x1. So because f prime at c equals 0, as we said, this is 0 all the way through, that means this must be 0, and f at x1 must be equal to f at x2. So pretty simple there. If you think that's almost too simple for words, well, the mean value theorem can be like that. One extra corollary, if f prime, okay, this one's important. Although it's simple, this one's important. If f prime equals g prime, that is, 2 functions have the same derivative in a section, then there's a constant c such that f at x equals g at x plus c. That means these 2 functions must be different only by a constant. If they have the same derivative, they must be different only by a constant. So to prove that, I'm going to make a new function, h equals f minus g. And if that's true, if h is equal to f minus g, if I took its derivative, h prime would then be f prime minus g prime. However, the original question said that f prime equals g prime. That means h prime must be 0. So this new function I've invented, h, equal to f minus g. When I look at that, and I do the derivative of it, I get f prime minus g prime. When we already just said at the start that in this particular case, f prime equals g prime. What I get from that is h prime equals 0. And that means that h prime, if h prime equals 0, from corollary 2 above, if h prime equals 0, then h must be some constant. If its derivative is 0, the h must be some constant. And that means f minus g, which is what that original function is, f minus g must be equal to some constant. And if I move that constant over, I get the result I'm looking for, is that f at x equals g at x plus c. That is, this function f at x must be equal to the other function g at x plus just a constant. So if their derivatives are the same, it means they must be only differ by a constant. And that result might have been fairly obvious before we even started, that you know that if two functions have the same derivative, they must be the same function, except for maybe a constant different. That's the only thing that can be different. Well, that's all very technical, and some people don't like those technical proofs, but let me just do a little example of that so you can sort of see what's going on. Find a function whose derivative is f at x equals 6x squared minus 3x plus 5, but the graph passes through 213. Okay, so I want to find this original function f at x, and all I know about it is its derivative is 6x squared minus 3x plus 5. Now I'm going to work backwards here to try and get this derivative. So looking at that 5, if that's the derivative came out to 5, then there must be a term in there of 5x. Yeah, the derivative of 5x is 5. So if I want the derivative to be 5, my original function, f at x, I used capital F there. We often do that in math, in calculus, is that if we've got a function that is the derivative, then we use capital F to say, here's the original function. Next one is, how do I get derivative negative 3x? Well, I know I need an x squared, but the derivative of x squared is only 2x, it's not negative 3x. So I think for a minute and go, well, what's going to make this play out right so that I get negative 3 as the coefficient there? Yeah, because what I've written there, the x squared, the derivative of x squared is 2x. But I need negative 3x. And it takes a lot of thought to come up with what's it going to take there. I mean, the first time you see one of these, it takes a lot of thought. We'll do a lot of these, and you get better at them. And then after a while, I go, well, okay, I'm going to have a 2 in the bottom, so that 2 cancels that 2, but I need negative 3 as the potential answer there. And the first time through that, you're like, whoa, that is some crazy thinking here. But I got to tell you, we're going to do so many of those, it's going to become sort of obvious. But take a look and let's see if it works. The first time you see one of these, just convince yourself that it works, and then you can sort of go, whoa, the first time you're doing this. Let's see, 2 times negative 3 halves would be negative 6 halves, which would be the negative 3. So this works. The derivative of this f is actually negative 3. And how about 6x squared? Well, I know I'm going to need an x cubed. If its derivative is going to be x squared, and I need a 6 out front, the one I've wrote would be, the derivative would be 3x squared, but I need 6x squared, so I guess I need a 2 out here. Okay, if you're not convinced, if you're like, this is all very confusing, let me just find that derivative, f prime at x. The derivative would be, okay, the derivative of 2x cubed is 6x squared. Oh, that's right. That's the derivative I'm looking for. See, the original, the f they gave me, they wanted the derivative to be 6x squared. So that works. So find the derivative of the next part. Negative 3 halves x squared times 2 would be negative 3x squared. Yes, it's the right derivative. And the final part would be plus 5. You see, I'm just trying to find the function whose derivative comes out to 6x squared minus 3x plus 5. And I just sort of played around with it the first time. Well, that function, that could be the function, or it could have any constant added to it. Any constant there would give the same derivative. So it could be like a plus 2, or a plus 5, or a plus 8, and I just put a plus c there saying any constant will work there, because when I take its derivative, I'm going to get 0. When I take the derivative of that constant, I'm going to get 0. So what I mean by that is there are many functions whose derivative is 6x squared minus 3x plus 5. That's from the corollary that I came up with over here at the bottom here. Corollary 3 says if two functions have the same derivative, they can be differed by a constant. I've said that this function has derivative 6x squared minus 3x 6x squared minus 3x. Oh, little mistake there. Little mistake there. see there. Let me just straighten it out. That's gone. Another one of those times where early in the video you might be like, well, what's going on there? That doesn't have an x squared there, but I fixed it afterwards. Okay. So that function has that derivative, and any function that differs by a constant will also have that derivative. They gave me one more piece of information. They said when x equals 2, y equals 13. So I can find that constant here. I can say, okay, 13 equals 2 times 2 cubed minus 3 halves times 2 squared plus 5 times 2 plus that constant. That point that they gave me allows me to find the constant that works here. So I get 13 equals, what do I get here? 16 minus 6 plus 10 plus c. If I move all that stuff over, I think I get the constant is -7. So I can be even more specific. The function I want is 2x cubed minus 3 halves x squared plus 5x minus 7. Two x cubed minus 3 halves x squared plus 5x minus 7. There's the function that does everything they wanted in this question. Its derivative will be 6x squared minus 3x plus 5, but it also goes through 213. See, this constant here could have been anything. Any constant out there would have gave the right derivative, but they wanted the specific one that also went through 213, so that was the extra information I needed to nail down what that constant was. I think actually this example is on the next page there, but I did it on the previous page. So there it is there. There's that actual example there. And this process that we just did here of finding what function gives the derivative we want is called finding the antiderivative. And there's got lots we're going to talk about antiderivative. And so that's what I did there is I said, okay, when they gave me the derivative function of f at x, I wanted to find the capital F at x function, whose derivative was what I'm trying to find there. So unlike all this time we've been finding derivatives, now this question asks us to find the antiderivative. That is, what function will give the proper derivative. And this process of finding an antiderivative is called antidifferentiation. We're going backwards here. Note, if a function has one derivative, it has many derivatives. Sorry, if a function has one antiderivative, it has many antiderivatives, and all of the functions that have that antiderivative, all those antiderivatives will be only differed by a constant. Well, this process is so important that we're going to find lots of antiderivatives, and so they asked me to do two new questions here. Oh, this was f at x equals sine 3x minus 2 e to the x was what that said there. And then there's, I'll do these on separate pages anyway, so let's just jump ahead to those two examples. This was f at x equals sine of 3x minus 2 e to the x. Sometimes those minus signs don't come through on PowerPoint very well. So it says find two antiderivatives of this. How are we going to find two different ones? Well, let's just talk about this. Let's talk about what would have to happen. What's the capital F function? What was the original function that gives this derivative? Okay, this is a little bit hard when you first see these. They have to really think these through. We're going to get good at them because we're going to do a lot of them coming up. But when you first see these take a lot of thought. That is, if the derivative comes out to sine of 3x, what was the original function? Well, it must have been cos of 3x to give derivative sine. But there's some major league problems here because as I've written it there, cos of 3x, its derivative would be, well, it's awful. It would be negative sine of 3x, not sine of 3x. So I'm going to need a negative out front there to fix that. And it's worse than that because by chain rule, I would have to multiply by 3 as well. So I'm going to need a 1/3 out there to deal with that 3 to end up with sine of 3x. You're like, whoa, what just happened there? Let's just see if it works first. And seeing that it works can help you think it through. The derivative of negative 1/3 cos of 3x would be negative 1/3 sine of 3x times negative 1 times 3. Strange. I'll do that in a second. I'll do that to check it. I'll do that in a second. I'm going to come down here and I'm going to go f prime at x and make sure what I did works. the derivative of negative 1/3 cos 3x would be negative 1/3 times negative sine of 3x times the derivative of the inside, which is 3. Does this work out to the original sine of 3x? Yeah, the two negatives cancel, and the 3 and the 1/3 cancel. And it could be after seeing that, you're like, oh, you're just trying to find a function whose derivative is sine of 3x, so I just have to play with the coefficients to make it work out. And maybe you want to rewind the video now and watch the original thinking again about how I came up with those things. Now, the second part is easier. What function gives derivative 2e to the x? Well, e to the x is very well behaved, so I get negative 2e to the x. However, any function that has the same derivative will be differ by a constant. So there could be a constant out here. There could be some number out here. It could be like a +2 or a +5, and it'll still have the same derivative. So here are my two functions I'm going to use. Okay, the first function I'm going to use is like negative 1/3 cos 3x minus 2e to the x plus 10. I'm just going to put a plus 10 out there. And that will have the right derivative because the derivative of 10 is 0. So that will have that sine 3x minus 2e to the x as a derivative. So another function I can use any constant I want out there. Again, negative 1/3 cos 3x minus 2e to the x minus 5. You know, any constant out there will do. And those will still have the right derivative. And I write those derivatives down here. All those functions, sorry, both of those functions will have the same derivative. They'll have the derivative sine 3x minus 2e to the x, because that constant, every time I take that derivative of that constant, I get 0. And so let me just review corollary 3. If a function has the same derivative, if two functions have the same derivative, the only difference between them will be that constant at the end. The main part of the function will be the same, but the constant could be different. Okay, some tough examples here. Last example coming up. An object is thrown downward from a height of 10. If the acceleration due to gravity is 9.8, determine the equation for the object's height. Ooh, great throat for you physics people here. And we're going to use antiderivatives to get the answer. That is, I know that the acceleration is negative 9.8. See, this is 9.8 downward. Due to gravity, it's going downward. So I get negative 9.8. So if I want to know the velocity function, I want to know which function has its derivative negative 9.8. So what function could I write down whose derivative would be negative 9.8? Well, it would have to be negative 9.8t. Well, that's right. The derivative of negative 9.8t is negative 9.8. So I know that the velocity function is negative 9.8t, but I just don't know if there's a constant out here. There could be a constant as well, because any number I put out there, like a +5 or a -9, its derivative will be 0. So I don't really know for sure what that constant is. I know the velocity function will be negative 9.8t, because that'll give derivative negative 9.8, but I don't know if there's also a constant out there. But that's not what they wanted. They wanted the height function. So I got to do this process again. I got to do antiderivative again and say, okay, what's the antiderivative of negative 9.8t? Well, I know it's got to have a t squared in it, because the derivative of t squared is 2t, and that gives me the t I want. But what's the number out front got to be to get negative 9.8? See, I'm going to multiply this 2 by whatever's out front, and I end up with negative 9.8. So I got to think for a second and go, okay, what number out front do I multiply by 2 and get negative 9.8? And it's negative 4.9. And you might have seen that in previous courses, that number out front is always negative 4.9 when we do objects on the Earth type questions. Let's just check if that's right. 2 times negative 4.9 is negative 9.8. And then the power reduces by 1, and I get t. So yeah, this is the right antiderivative. Then there's plus c times t, because the derivative of ct is just c. See, if that's a 5, then it would be 5t. If it's a 10, it'd be 10t. I don't really know what that is. Plus another constant. How am I going to write another constant here? So what you'll find as we do more of these is that we just start numbering the constants. This is c1, and then I get another constant here. Okay, if you're deeply confused right now, just take the derivative of h of t. The derivative of h of t would be negative 9.8t. The derivative of c1t is just c1, and the derivative of c2 is just 0. So as complicated as this looks, it's actually just simply finding a function whose derivative is negative 9.8t plus c1. For some constant. I just don't know what these constants are. Well, they gave me a little information here. I can find one of the constants. When t equals 0, h equals 10. So I know that 10 equals negative 4.9 times 0 squared plus c1 times 0 plus c2. So I can actually find that c2. c2 is 10. So I get my final equation. Well, not my final equation. It's still got an unknown in it. I don't know what this constant is, but I did find out what the second constant was. So there's the h at t function. We'd need a little more information to get that first constant in there. Now, if those last couple examples seemed really difficult, I say go backwards. Take the functions I ended with and take their derivative. And when you take their derivative, you'll get those original functions. And so this process of antiderivative, I don't want you to stress about it too much because we're going to do it so much you'll get so used to it. This is just the intro on this antiderivative stuff. So it just takes a little bit of practice to get to know it. And it's new and it's a little bit weird. And new things seem a lot harder than they are sometimes after you practice a little bit. So, some difficult ideas in that lesson. So definitely take a run at that homework, beat your head on it a little bit, get some clarification, ask some questions, and make sure that all that stuff all makes sense. Have a great day.